Well, welcome back and thanks for joining me. We're going to continue our discussion of energy, and this time we're going to talk about the difference between nuclear fission and nuclear fusion, two different very powerful energy sources. So in our past lesson we had talked about historically how we've changed our energy sources. You know, in the 1850s we would have used a lot of wood and coal, and then as we moved forward we got into a lot more coal because it seemed to be cheap, and we were using wood to build homes and other things. And by the 1940s we were using almost no wood for heating purposes or energy, and we were starting to add petroleum and natural gas. By the 1980s we were addicted to oil, and we had gotten rid of a lot of our coal because it was considered dirty for the environment. By the 1990s we started to have a little bit better mix because we were worried about the import of oil from the Middle East, and we started to build more nuclear power plants. And then we had some problems with some nuclear power plants, specifically Chernobyl in the Soviet Union. And then you can see as we move ahead to 2005, those numbers are changing yet again. And then we talked about where they are today. And so, you know, we still are very reliant on fossil fuels, and we get some of our energy from nuclear, some from renewable, and solar and geothermal, almost none. Now, in Illinois, I just did a quick Google search. It says we get 54% of our energy in Illinois from nuclear reactors. So 1/8 of the nation's total nuclear power comes from Illinois. And that's one of the reasons we're going to go through nuclear power, just to make sure as a citizen you understand the difference, what are the risks, and what are the benefits of that. We'll actually do a whole separate unit on that, a small mini unit after the atom. But for right now, I'm just going to introduce the difference between fission and fusion. So, both nuclear fission and nuclear fusion are nuclear reactors. That means the word nuclear comes from the fact that it changes the nucleus of the atom. The nucleus is really the identity of the atom. If you know the number of protons in an atom, you know the element. So it's kind of like we're changing its personality, I suppose, if we can personify it that way. There are very large amounts of energy released through both nuclear fission and nuclear fusion. Albert Einstein kind of taught us how to do that calculation, E equals mc squared. We'll talk more about that later, although I won't have you do any of those calculations for me on a quiz or any test of any sort. Both nuclear fission and nuclear fusion have transmutation. So even though we say in chemistry it's not possible to change one element into another by a chemical reaction, by a nuclear reaction it is possible for one element to change into another, and that's what the term transmutation means. Now, fusion is what happens on stars like the sun. That's how it makes its energy. It takes very small atoms like hydrogen and it melts them together at incredibly high temperatures into larger elements like helium. So when you melt elements together, that's called fusion. You're welding or kind of like fusing them together. Now, the advantage of fusion over fission is that there is no radioactive waste that has to be stored. We'll learn that much of that radioactive waste lasts for millions or at least hundreds of thousands of years, and it has to be stored as not to harm people. The other disadvantage of fusion, why we can't really do it here on Earth effectively, it takes really high temperatures, like around 5 million degrees Celsius, in order for this to happen. And we just don't have materials that can withstand that sort of temperature. Now, fission, on the other hand, is what we can do here on Earth. It is done in nuclear power plants where we split very large atoms, like isotopes of uranium-235. It's a specific type of uranium. All uranium wouldn't be fissionable. It does produce radioactive waste that has to be stored for, as I mentioned, hundreds of thousands of years. And this is how we get our energy from nuclear power plants. So let's kind of talk about both of these. On your test at this point, what you're going to need to know about is fission is splitting of large atoms, and there's no radioactive, and there is radioactive waste. And fusion is taking small atoms, melting together, and there is no radioactive waste for that. So let's talk about this. This was an ad I saw in some magazine years ago. So there's only one thing worse than spam, irradiated spam, right? Now, you have to understand, well, first of all, spam is a meat product from Hormel. They say it stands for spiced ham. I say it stands for slaughterhouse processed amalgamated meat. You know, chunks of meat all ground up and bone in there. Anyway, if you are against nuclear energy, you're going to look at every single place it's used and make it look bad. Now, it turns out that irradiation of food is actually something that we learned in the 1950s. After the World War II, it was applied to food to save lives. It actually, by irradiating the food with a very high energy radiation, you basically sterilize it, kill all the bacteria on it, and then the radiation that they use has a very short half-life. It's gone by the time that food comes to you, and basically when you open up that can of Spam, it's about as sterile as a Band-Aid, which is good. That saves lives, but people are going to twist it, and they're going to selectively give you facts to promote that agenda of fear that nuclear energy is all bad, right? It might be they're against eating animals. I don't know, against meat. You always have to look at who's funding. What is the bias behind something? Look, if right now we're coming up on an election, depending on what your belief system is, if you watch CNN, you think Biden is godlike. If you watch Fox, you think Trump is godlike. Probably neither is true. Both of them selectively give facts and information, and as a consumer, you should probably watch more than just one of those channels to get a truer picture of what's going on around the world. So irradiation can be a good thing. Let's assume that, and I hope this never happens, you develop some sort of cancer, right? Oftentimes they'll give you chemotherapy, and chemotherapy is often a mixture, a cocktail of drinks that you might have, or injections, or radiation, and they're used to hopefully shrink the tumor that's growing inside you. Again, I would say this is a good use of radiation, right? You need to have a little bit of UV light radiation to absorb vitamin D, so you don't develop rickets. These are, again, radiation isn't good or bad. How we use it, the amount we get, that's a little bit different. How can we protect ourselves from radiation? Well, it turns out there's different types of radiation. For this first test on matter and energy, I'm not going to ask you about alpha, beta, and gamma, but they are different types. And an alpha particle can be stopped by merely a sheet of paper. Beta particles, you'd need quite a bit of wood would stop it. And gamma rays will go right through brick, and you would need something like lead or concrete, pretty thick actually, to protect you from all that radiation. All right, so let's get down to brass tacks, as they say. So in nuclear fission, you are going to split a large atom. So in my graphic here, I start with a neutron. And in the nucleus, there's protons, neutrons, and electrons are outside the nucleus of the atom. But if you were to slam a neutron into fissionable uranium, and they've had to separate this to get it to be the right kind, right? Like they have to separate out the good uranium that's fissionable versus the non-fissionable uranium. And they do that using a centrifuge and separate it out by mass. So if you're lucky enough and you get this right, the neutron slams into and joins in the nucleus, making that nucleus unstable. At that point, that unstable nucleus spontaneously rips apart and fission occurs, or splitting. And so that uranium, now it's no longer uranium-235, it's called uranium-236, splits and turns into daughter isotopes of krypton and barium. And oh, by the way, if you were to add up 92 and 141, you would indeed get that 236 right here. Okay? Now you're like, no you don't. 141 and 92, and you pull out your calculator. Well, we got to do a little bit of math on that one to talk about it. The big idea here is big atoms split by hitting with a neutron, and then they release energy, and then three more neutrons are released that can then hit more uraniums and start a nuclear chain reaction. So that's what I'm showing you here. I've got a neutron hitting our uranium-235, producing those daughter isotopes. It also produced 3 more neutrons that hit additional isotopes of uranium that cause those to split, giving off additional neutrons, and this chain reaction goes from just the start of just one fission, then makes millions and millions of fissions in a very quick period of time. So it's kind of like pushing over one domino, and then they all start to fall over afterwards. And the way you can control these nuclear reactions is simply absorbing neutrons. And again, that we will study in the nuclear chapter. At this point, the big idea is nuclear fission is big atoms splitting into smaller atoms and releasing energy. And with that is radiation also being released. All right. If we were to look at, this is a map obviously of the United States, and the little red dots represent every nuclear power plant here in America. And if you look, there is a huge concentration. There's actually 11 nuclear reactors in Illinois. That's more in Illinois than any other country of the world, which is why we get more than 50% of our energy here in Illinois from nuclear power. Now, when nuclear power was discovered in terms of these nuclear reactions, let's talk about in World War II developing an atomic bomb. Enrico Fermi was in charge. He was an Italian physicist. He came to America. I believe he taught at one of the Ivy League schools, Dartmouth or one of those. And he was tapped to be in charge of the Manhattan Project. And that was to develop the bomb. And the problem is they were building a bomb that they didn't understand fully the power of that thing. They didn't know if they started to split atoms, if it would actually cause, the world to come to an end, if it would not stop, right? Or if they're doing fusion, if they would start to fuse together all the atoms in the world and it wouldn't stop. In either case, they had a problem. So Enrico Fermi came up with this method of solving the problem. He called it a Fermi Approximation, where you don't know the answer to a question, but you make an educated guess based on a bunch of series of calculations of things you actually do know about to get a reasonable answer to the question that cannot be answered any other way. And he concluded that you could make a bomb that would not ruin the entire planet. So they went ahead with it. Now let me give you a simple example of a Fermi approximation. So I could ask the question, how many piano tuners are there in New York City? Now, there's no way for you to know that answer. Sometimes people say, well, I'll give you an answer. I'll say there's 200 piano tuners. Now, am I right? Well, I think I'm pretty close. Now, did I look it up online? No. You're not going to find everyone online because, first of all, every piano tuner may not be listed, right? You can't look it up in the yellow pages, the old phone book, right? Because they might not pay for the ad. So how do we get that answer of 200 piano tuners? Well, let's look. I did actually a Google search just for giggles. And I did, how many piano tuners in New York City? It says, we know there are probably more than 100, but almost definitely less than 1,000. And I would agree with that because when you do a Fermi approximation, you're going to get, within an order of magnitude, a pretty close answer. So how did I get my answer? Let's look. So the first thing I did is I assumed the population of New York City is 10 million. I looked it up, it's 8.399 million, but 10 million is close enough. I then did a quick poll in my class where I asked how many of your families have a piano. And let's go a step before that. I'm assuming on average there's 4 people in a family. I know there are some families that do not have children. There are some that have only a single child, and there's some that have 5 children or more. Right? I'm just saying on average 4 people per family. So that means 2.5 million families. So then I polled my class, and they said, about 1 out of 5 people have a piano in their home. So divide 2.5 million by 5. So you have about 500,000 pianos in New York City that need to be tuned. Each piano, according to the tuner, should be tuned every 6 months, but people aren't wasting that much money. Realistically, maybe every 2 years they're going to tune their piano. So that means I took 500,000 and divided there. We've got by 2, we got 250,000 pianos that need to be tuned annually in New York City. Now, most of them don't need a full-blown, rebuild that might take all day. They're just going in and tuning it. So perhaps if they're ambitious, they can tune 5 pianos each day. That would mean we'd have 50,000 days of work per year. Now, assuming a piano tuner is working full-time, they might work 250 days per year. I know there's more days in the year, but people take off for weekends and holidays. So that would mean we would need about 200 piano tuners. Would be a pretty reasonable Fermi approximation of how many piano tuners in New York City. Now, I show you Fermi approximations because sometimes when we work problems in chemistry class, you might type something in wrong on your calculator and you get an answer that makes no sense, right? When you look at a problem, make a best guess judgment. I call it thin slicing. Just what's your first gut tell you the answer should be around? And then calculate it. And if your answer is not anywhere close to that, either your original thought was wrong or you've made a calculator error. So Fermi approximations are somewhat useful. I used to give you an assignment like figure out how many baseballs need to be ordered for if you're the Cubs manager for an entire season, and then I would joke like, well, they never make it to the playoffs, so you don't have to worry about that, even though I'm a Cubs fan, right? And then you got to remember you only play half the games are away, half are home, and you could come up with a reasonable answer, or how many cows need to be slaughtered each day in America to, just for McDonald's to give away, to sell all their hamburgers, and you could very quickly figure out how many cows that is, and it's a large number, but we won't waste the time doing those this year. All right, let's keep moving here. All right, so fission, remember, is a big atom splitting into smaller atoms. Fusion, on the other hand, is small atoms that are going to be melted together into a slightly bigger atom. So here I have 4 hydrogen nuclei. That's just the nucleus of the atom, right? Those are called protons. And then I'm going to melt them together with these beta particles. These are called electrons. And then they form a helium nucleus. And then they release energy. And this is what happens on the sun. So I take small atoms and melt them together to make a bigger atom. Now, probably this would have looked a little bit nicer if I made this bigger for you, but nevertheless, that's what fusion is. And remember, this takes really high temperatures, like 5 million degrees. Now, I'm going to go through some very, very simple math here. You are not responsible for this math, but I just want to kind of go through it real quick. We understand that cornerstone, a fundamental idea in science, is the conservation of mass. Mass is, neither destroyed or made, right? But mass can be converted into energy using Einstein's E equals mc squared. E equals energy, m is mass, well, it's actually the mass defect, we'll talk about what that means, and c is the speed of light, 3 times 10 to the 8th meters per second. Now, if you were to take 2 hydrogen molecules, that's 4 atoms of hydrogen. Here's hydrogen on the periodic table. It weighs 1.008 atomic mass units, or AMUs. It's not an AMU. That's the sound a cow makes. This is an atomic mass unit. 4 times 1.008 is 4.032 AMU. Now, if I take the mass of 1 helium, it's 4.0026 AMU. Now, excuse me, these two masses are not equal. Somehow we've lost mass going from 4 hydrogens to 1 helium. That lost mass, that 0.0294 AMU, that's called the mass defect. Now, if you convert that into kilograms and multiply it by the speed of light, you end up with the amount of joules of energy released for that reaction. And that's where nuclear energy is occurring with this fusion reaction. It is actually mass literally be converted into energy. All right, and this only happens in nuclear reactions. Just a small amount, a handful of fusionable material would be enough to make an incredible amount of energy. And that's how the sun is so bright and has been burning for so long. I'm not going to go through time travel with Einstein. When we do the nuclear unit, I might talk a little bit about black holes, and I have a fun little story there I'll share with you, but for right now I'm going to skip that because it will not be on your test. I want to talk about man's attempt at fusion here on Earth. Now, I mentioned at the very beginning that there's no materials that can withstand, 5 million degrees Celsius. However, when you pass electricity through wires, it creates and induces a magnetic field. And that magnetic force field has no melting point. So at Princeton, New Jersey, probably 30 years ago, they came up with what was called the Tokamak Reactor. Tokamak is a Russian word meaning toroidal or donut shaped. And so there's a giant ring of wires going around, and you can see here's a guy standing on the inside of this giant thing of wires. And electricity goes through those wires, and it creates a magnetic field that can then withstand the temperatures of 10 million degrees Celsius. Now, that magnetic field then is what we call plasma, this high energy radiation field that can hold it. This fusion reactor, it works. The problem is the amount of energy that it takes to create the plasma field is more than you get out from the actual fusion reactor. So it's a neat idea, but it's not going to work. So the idea is, can we do cold fusion, fusion at a temperature much closer to room temperature, or at least that materials can handle, rather than 10 million degrees Celsius? Well, it turns out two gentlemen, I don't know if you can read the year on here, I think it says 1989, came up with cold fusion. And it made, here it is on the cover of Time magazine, Stanley Pons and Martin Fleischmann, two obscure chemists stirred excitement and outrage in the scientific world. Now, they had claimed that they had figured out fusion in the lab that could be done at close to room temperature. Now, if you're an investor, that is a very exciting opportunity for you. So instead of the normal process of when you discover something, you write up your results, you publish it, you have other scientists repeat it, and then you go ahead and get it published, and then you go to the media. They went directly to the media. And they must have had something there, because it took probably 6 months for the frenzy to die down, and realize that it wasn't really what they thought. Right? There was something else going on. So still to this day, we cannot do cold fusion. It still requires very, very, very high temperatures. Now, it turns out that I'm guessing that Stanley Pons and Martin Fleischmann might not have too great of reputation. If they write grants nowadays, they might not get those grants because of their erroneous reporting of data earlier in their careers. So you want to be very careful of that. Alright, we had mentioned about the half-life of radiation produced when we do fission or splitting of large atoms. So it turns out that you start with a certain amount of radioactive material. After a certain period of time, half of those radioactive particles go away. That's called its half-life, the time it takes for half of the material to dissipate. You wait another half-life, it's not all gone. Half of the 50% is gone. Now you're down to 25%. After 2 half-lives, you wait another half-life, you're down to 12.5%, and so on, and so on, and so on. And after about 7 to 8 half-lives, we assume that the material is pretty much safely all gone. So if we start with, this number of radioactive isotopes, after 1 half-life, that's cut in half. After 2, that's cut in half. After 3, it's cut in half, and so on. All right, so let's talk a little bit more about energy, and because we're near the very end of this unit, and it's called matter and energy. So I should have put the slide again just to remind you to go back and look at what's the difference between fission and fusion, because you'll have to be able to answer those questions on the test. All right, we know that energy is conserved in chemical reactions, so I'm kind of contrasting with you nuclear reactions, right? And in nuclear reactions, energy is all accounted for. It just changes form from mass to energy. But in a chemical reaction, it's just energy. So here we're looking at, this is generally a reaction I would do for you in class. I would combine hydrogen and oxygen. I would light a match, and it would explode loudly, and it would produce a little bit of water vapor and release energy. And the atoms are rearranging. Here we have H2 plus H2, 2 H2s, and an O2. They get rearranged into H2O and H2O, 2 waters, and energy. Here's another one. and I'll show you a little video that goes along with this one, so it makes it a little bit more exciting for you. Well, I guess this one, it's going to be the next one I do that for. If we were to look at the energy of the reactants over here, it has a certain amount of potential energy stored in those chemicals. And if I look to the energy of the water, it has a little bit less energy. But if I were to do this in a flask and put a rubber stopper on top and light it, I would shoot the flask up. It would be projected up toward the ceiling. It would also make a loud bang, give off some heat and a little bit of light. If I were to add up the energy of the stopper moving, plus the energy of the heat given off, plus the energy of the light, plus the energy of the sound, all of those things, energy of carbon dioxide, water, stopper, heat, light, and sound, would be exactly equal to the energy of the acetylene and oxygen that I started with. Okay? So let's look at that reaction. So I found this video clip from Flint Scientific. I'll go ahead and play it. I'm going to take my earbuds out so hopefully you can hear this. All right, I'll go ahead and stop that. So what she was doing then was taking a little bit of acetylene, well at this point it's not acetylene, this is called calcium carbide she was taking. I'm not showing that equation. But then when she put it in water, that stuff generated this acetylene gas. That combined with oxygen, and when she lit a match, it produced carbon dioxide water and produced the energy that caused that stopper to go flying up. So the idea that energy has to be conserved, that's a law. That's a law. That never changes. Energy is always accounted for. There are some objectives for you. You know, you're welcome to read through those. These were on the PowerPoint slide. I'm not going to read them to you. You can pause if you need to. There's some objectives for energy, again, because we're talking about matter and energy in this unit. So that concludes this unit. If you have questions, please go ahead and send them to me. We'll have some time to talk and see if you have specific questions at our Google Meet. Thanks for joining me. Have a good day. Bye-bye.